So as you can see, the title of our talk today, which will be focusing on solving optimization problems with MATLAB. Okay. Uh, Now the agenda for till 12:30 looks like this. So we will have some introduction on what we are going to do today. We'll look at some of the type of optimization problems like least squares minimization, nonlinear optimization, mixed integer programming, global optimization. So these are some popular topics in the area of optimization, and they are widely used in different applications. I'll also talk about few applications. Okay, so let's get into the introduction part. Okay. So, what are some optimization problems we see around us? Okay, so if I've taken multiple examples from different areas, for example, if you would like to maximize fuel efficiency in your cars, okay, everybody drives cars, bikes, different vehicles, right? So we would want them to give maximum fuel economy. Okay, so we want more kilometers per liter of fuel. Okay. That is an optimization problem because there are many parameters that define that system. Okay, so we'll look at some of those areas. Another area is also minimizing risk. This is specifically for people who are working in the finance area. So you have different stocks, different options. That how do you balance out those different stocks and options? Okay, to minimize risk. That's again a kind of an optimization problem. Okay. Then you have let's say some other customized problem of your own. In that case, you might be working to maximize your profits or minimize your investment, and so and so. Okay, so these are some common problems that we have listed out here. Okay. Now, if you think about how these design process happen, for the optimization problem as a whole from bigger perspective. Okay, so we normally start with initial design variables. What are our design variables that basically drive our system? A system could be an electrical system, mechanical system, multi-domain system. Okay, so this is what we are trying to optimize. Now, once these design variables go into that system, okay, the objectives that we have defined, either to minimize something or to maximize something, okay, we check whether these objectives are met or not. Okay, so if these objectives are met, straight away we have an optimal design. Okay, we have an optimal design, and we can use that variables. Now, but that is not the case in many systems. If we look around, whenever we start with our initial variables, they don't go to an optimal design. Okay, we will have to find variables which makes our system optimal. Okay, so in that case, no, and then we modify design variables and redo and reiterate these process. Okay, that is how we do it. Okay, so this can be done manually by hit and trial, but in some cases you might get a good optimal solution, and in some cases you might not get. Okay, and you might get a local solution. Some cases where you might be missing out with a global solution. Okay, and we'll see what are these local solutions and what are these global solutions. Okay, so why do we do optimization? Okay, so that's a very maybe a lot of you might already be familiar with this technique of optimization. So you might already be knowing all these things, but it's good to always brush our memories and see why do we use optimization. Okay, so if you see in this graph, we have a graph of basically on the x-axis the engine RPM. So if you remember, we take an example of maximizing your fuel economy. Okay, so the x-axis is basically nothing but the RPM of the engine. On your y-axis, you see the pressure ratio of that engine. Okay, and you see this color fringe. Okay, so what does that indicate is that indicates your fuel economy. Okay, where the fuel economy is maximum. Okay, so blue color is low, and the darker the red goes, it is basically more economic. Okay, so what do we do is manually, if you see this process, we take an initial guess. So we take an initial guess of 3,500 RPM at 0.5 pressure. What is the fuel economy? Okay. Then what we do is we can start manually changing the RPM and changing the pressure ratio. Okay. And then we keep trying different options, and we say, okay, this is bad. Okay. Now, if you see this graph that you see on the screen right now, okay, that is not available typically. Okay, that is just shown here for representation, but that is not how you will basically go about this manually. Manually, you are just blind. Okay, you'll have to just take few guesses and you just keep trying. Okay, so it just in this graph you see the manual guess overlaid on the actual scenario. Okay, so what we are saying is, if we are keeping the RPM fixed and we are changing the pressure, we are actually increasing your fuel efficiency. Okay, so what you can see is that if I keep the RPM constant, go above, and increase the pressure ratio, we get this point, okay, which is maximum fuel economy. So and if we go above that, we will not have a maximum fuel economy. Okay, so what we see is, okay, this is good fuel economy for me. Okay, but clearly from this graph, what you can see is that if the person is playing in the blind, he will not be able to find this point. Okay, and that is the point where the maximum efficiency is. Okay, inside this region. Okay, this particular region is the maximum efficiency. Okay, so that is, if you see, if we do manual optimizations, we might get some optimized design, but that may not be the perfect solution. Okay, so now how do you overcome these concepts? Okay, and instead of using manual, we approach through systematic algorithms, which are part of optimization design. Okay, now if you see, if we use proper optimization techniques, okay, and that means various algorithms in optimization, you might have already gone through some of those algorithms in last few days. Okay, so clearly what we can see is, when those algorithms work on this problem statement, okay, the initial guess is same. Okay, and clearly what we see is that the next guess the algorithm takes, it starts getting closer and closer. Okay, and obviously the algorithms have found the right solution, as you can see, which is in the center of this graph. Okay, so this shows that using proper optimization techniques is far more better than manually doing optimizations. Okay, so that is what we can see from here. Okay, okay, then so when we start, we understand, the optimization is necessary. Why use optimization? So we need to find better designs. Now we might design something, but then that might not be optimal or efficient in terms of the weight, in terms of the energy consumption, in terms of the performance, in different things. Okay, we need to also do faster design evaluation. So that what it means is that you need to evaluate multiple designs and check them whether they are right for your requirements. Okay, trade-offs. Okay, and the last one is basically non-intuitive designs also can be found out from this optimization. Something that is intuitive, you might think about it, but something like which is non-intuitive can also be found. Okay, so for example, if you see on your right here, there is a picture. Okay, and what that picture is all about is, it's a type of an antenna. Okay, which was designed using genetic algorithm. Okay, again, that's a type of optimization algorithm. Okay, we'll go deeper into that. Okay, just to show you what is the value of using these algorithms. Okay, so the value of using such algorithms is that people, so these are basically electrical electronics engineers. What they did is basically they said, they want to maximize the let's say radiation from an antenna. Okay, so they created the whole problem statement. So formulating the optimization problem statement is a very important task. Okay, so that's also very important. So we'll see how to formulate a optimization problem. Okay, so in this particular example of antenna design, they formulated the statement, and then they gave it to the genetic algorithm optimization, and this is what the 3D structure it has found out. And this is what it makes really valuable. Now they can directly test this antenna and see whether it matches the requirements or not. Instead of manually doing it in trial, this makes it more shorter as a design time. Okay. So that was just introduction and understanding what these optimization designs look like and why to use them. What are some applications we can use it? Okay. So what we'll do is we'll quickly go into the least squares minimization. I believe you have already seen this earlier in the days, but we can just cover it quickly so that you can maybe there are some new things also that we can uncover from here. Okay. So curve fitting demo, some things which you already seen, I can also skip it because curve fitting, I believe, I think Professor Dhami was saying he might have covered in that. Okay, so just to brush up in this is basically what is curve fitting basically. Okay, so there are points, for example here x and y points. X is basically time, and y is some values, and what we would like to do is fit a curve on these points. Okay, and why it is useful is so that once we fit a curve on it, we can predict inside values, and if you interpolate outside, we can do outside values also. Okay, so this is useful when you have data. Okay, and why do we do these things is because we can use that data to create parametric equations, which is basically here exponential equation here. You see C1 plus C2 e to the power minus t. Okay, so what is going to help you is with basically predict something inside those points or outside those points. Okay, so for example, if you are working with a let's say example a motor. Okay, so you can collect points from the motor, what voltage goes in, what angle it rotates or what speed it rotates. Okay, and if you collect 10 such points, what you can do is you can actually create a model of your motor. Okay, without actually going inside the motor aspects. Okay, so that is the value of using curve fitting. Okay, now just quickly I'll show you the program as well. Okay, so let me go into MATLAB now. Okay, so I have this MATLAB here. Let me open my examples from here. Okay, so these examples I have also given here. Anybody wants it, they can just request them, and you can get access to these examples. Okay, so there are a lot of examples. I'll show you what examples we have in this. Okay, so what I do is if somebody has a curiosity what I'm doing. Okay, so basically what I've done is, instead of opening, when I'm opening a lot of examples from here, so you see I have an HTML page here. Okay, and basically all my example is here in this folder. Okay, you see I have a least squares, nonlinear example, gantry crane. I'll take some examples also. Traveling salesman, multi-start nonlinear, regression, global optimization peaks, GA circuit design, right? Mount Washington. There is a mountain, and you want to say, how do I reach to the top through the shortest path? Which is that shortest path? Okay, that is also we can find out. Okay, or which is the highest point, which is like let's say lowest point, all those things. Okay, so what I'm doing is basically I've created a MATLAB program here. Okay, so what I do is basically add paths here. I can define all the shortcuts so that I can save a lot of time. So if you're also using MATLAB to present multiple things at conference or something, you can also use similar techniques. So this MATLAB script is also along with this, so you can directly see how to do it. So you can also replicate it your end. Okay, so what I'll do is, so if I click on this link, it directly opens me that particular program. Okay? So that's the benefit of doing this HTML page. Okay, Now here you see this is a MATLAB program, and this is what we were talking here earlier. Okay, let me go back to this one. Okay. So how does a MATLAB program look for this example? So you can define your variables T like a matrix. Okay, so it's a vector or a matrix. Okay, it's a one dimension. Y is a again a one-dimensional matrix. Okay, and then you can see a plot of it. Okay, if you want, I can quickly run this. Okay, so okay, let me go on the top first. Okay. So all these percentages, you see double percentages here. Okay, let me go on top. So these creates basically comments plus sections in your code. Okay, so I can run one part by one part. Okay, so for example, if I start from here, I can say run and advance. Okay, so run. So this has executed. It is waiting for me to run again. Okay, so when I click on this, it shows me all the points that we have. Okay. Clearly from these points we can see that it's an exponential curve, okay, visually. Okay, and what we're going to do is now we can keep this minimized. Okay, run. So we can add titles and all those from command line also. That is also you can do. Okay, because not just a graph does not make some meaning out of it. So you have to add some context to it. What is the x-axis? What is the title? All those things. Okay. Now, since we know that this is exponential, we are directly going to set up a linear equation and find out the coefficients of it. Okay, like C1 and C2 with that we saw here. Okay, this is the linear equation that we are talking about. Okay, so we'll find the C1 and C2 coefficients here. Okay, so that is what we have started with. Okay, so let's do that. Okay, and this is what you will see. Okay, let me open that. Okay. So right now we have not plotted that equation here. Okay, but before we do that, okay, what is also important is also to understand which solvers to use, how to use them also. Okay, so let me open the documentation of this optimization toolbox. Okay, so if you go here, you will have getting started. Okay, so there you can also go and learn about this tool. Okay, before that, if you see here this link, okay, optimization problem setup, choose solvers, all that. Okay, so let's get into this. Okay, choosing a solver. Okay, from here what you can see is there are different types of solvers that you can use here. Okay, so if you click on this Optim tool, okay, and what you will see is that there you'll be shown with the multiple solvers here. Okay, so Optim tool is basically a graphical interface which allows you to set up the problem graphically. Okay, and what does it do? Let me open that. Okay, so I can type in Optim tool like that into the command prompt. Okay, you can also, in the new versions, you can go to apps, and there also you can find this. Okay, so you can go to apps, and if you look on this, and you see optimization. Okay, so here you see optimization. Okay, so from here also you can launch it. Okay, and you see here it's showing the same name, Optim tool. Okay, so what does it do? So you can click on it. It's going to open that interface. Okay, so this interface allows you to solve different types of problems. Okay, if it is a constrained nonlinear minimization, min-max optimization. Okay, fsolve, fmin solve. Okay, so everything is available here. Okay, so you can use one of the solvers that fits into your problem statement. Okay, and then you can define all the constraints and the problem itself, functions, all those things here. Okay, and then you can actually start solving this. Okay, so either way is fine. If you use MATLAB script, that's also okay. If you use a GUI, that's also okay. Benefit of using GUI is, for example, you can also generate code from here. Okay, so you can see here when let's say you don't want to write a lot of MATLAB code. Okay, so you just put what is your objective function, start point, your constraints, all those things, you can go to file and say generate code. Okay. So what is it's going to do is it's going to write a MATLAB code for you. Okay, and that you can edit yourself. Okay, that's the useful feature of this. Okay, so let's go here, go back. Okay, so now what we're going to do is find those coefficients. So we have found those coefficients, and what are these coefficients? We can see it. So these are basically two C1 and C2. Okay, so we have found those two coefficients. Okay, now if we use these coefficients inside our curve fitting and try to plot it, okay, so what we will see is that we'll get this kind of plot. Okay, so we started with the points. We created an exponential equation. We found the coefficients using optimization, and now what we have done is plotted it. So we can clearly see how is the curve fitted model. Okay, okay, so that is what we do now. So here there is no constraints. Okay, it is just found those coefficients and we have plotted it. Okay, sometimes what we have is also constraints in the our problem statement. Okay, so those constraints could be such that, for example, the resistance in our system cannot go negative or zero. Okay, so R cannot be less than let's say 0. That is our constraint. So these are all, because these are mathematical functions. Okay, and if you are working on a real life problem, they have to be driven by basically what can be values. Let's say can go below 0, above 0, all those things. Like resistance can't go below 0, negative resistance not there. Or let's say your material that you're using cannot have such certain properties, or cannot have certain thickness, things like that. Okay, so all these are basically these constraints come in, become converted into a mathematical function. Okay, that is what is important. Okay, so what you see is that we can actually create constraints, like this. For example, we are using here ls lq qln in. If you have seen this earlier, okay, you might have seen this because this is, I think, already covered. So this is basically a type of, let's say, your constraint. Okay, linear constraint. Okay, so we can apply different kinds of constraints on it. Okay, and this is how you apply that constraints. Okay, so what you do is, as earlier we use without constraints, this time what we are going to say is use the optimization tool to solve this with this constraint type. Okay, and this algorithm. Okay, interior point algorithm. Okay, and this is also there when you saw the optim tool. Okay, there also you could see that. Okay, so let's put these constraints here. Okay, we can put these constraints and check fitting again. Okay, so we can see the curve fit model here. So what you will see is that it looks pretty much the same graph. Okay, but if I zoom it a little further, okay, over especially on the top part, okay, this part, so you will see that there are basically two graphs here. Okay, one is with constraint, other is without constraint. Okay, so the constraint does make a lot of difference on the way the coefficients will be calculated, because they are now constrained to look into certain bounds only. Okay, so this is also a very important aspect, and you can also put constraints into your system and find the optimal C1 and C2 in this case. Okay, so these are the design variables, C1, C2. They look mathematical, but they actually can represent something physically also. Something like a motor, resistor, capacitor, anything. Okay, that can be represented very easily. Okay, so these programs, if you're trying to write your program, okay, this program we can actually give it to you, so you don't have to worry about how to write this program, and if you're not able to follow this program. Okay, but if you do want to follow this, you can actually type all these commands. Okay, and you can get this done very easily. Okay, So you can define your own variables, your own plotting. Okay. So that we can give it to you. Okay. If you're worried about the programs, that these programs will be given to you, all the files and folders. Okay. And you can do it at your own end, because then what will happen is, if I go one by one, you might not be able to cover all the things. Okay. That's okay. Presentation, I'll go slow. Okay. All right. So let's get into the next one here. Okay. So this is what we did in the program. Okay. So we had a linear system of equations. Okay. We found out that there are two coefficients that we wanted to find. Okay. And this is how we used the optimization, that's a solver to basically find all these 2 points. Okay. All right. So, okay. Now we get into another type of problem. Okay. That is basically nonlinear optimization. Okay. What we saw was these systems can be linear, sometimes they can be nonlinear. And once they go from linear to nonlinear, things change a lot. Okay, because the systems become slightly complicated because of nonlinearity in the system. Okay, some of the examples of let's say nonlinear systems are, let's say, a nonlinear spring in mechanical domain. There are nonlinear resistors, nonlinear capacitors in electrical system. So you can think of different systems. Like very popular example of a nonlinear system is something like battery. Everybody has a phone or has a laptop, and they have basically a battery in it. Okay, so battery has a lot of chemistry going inside. Okay, and most of these chemical processes are highly nonlinear and difficult to capture. Okay, so that's why dealing with nonlinear, when we work in real life, mostly systems are very nonlinear type. Okay, so for example, you buy a new phone, and it might discharge on the same conditions in 2 hours, or if it is a hotter day by 5 degrees, it might discharge in 30 minutes, 40 minutes also, right? So that is what nonlinearity is. So something that is not going linear with input variables or design variables. Okay, fine. So we'll get into this problem. Okay, so in this case, what you can see is, let me read about this problem slightly. Okay, so what it contains is basically, so here is the problem. Okay, let me go to that one. It went to this earlier one. Okay, this one. Okay, so in this particular example, what you see is an equation here. Okay, so we would like to minimize the function shown here. Okay, so it's a logarithmic function. Okay, so there are nonlinear terms in this equation. For example, if you see here, this one here, there is a quadrat third degree equation here. Okay, so since this is a 2 variable function, okay, so there's a 2 variable function here, x1 and x2. Okay, there are 2 variables inside. Okay, what we're going to do is this can be evaluated very quickly. That means it can run fast. You know, I can just put in these numbers x1 and x2, and you can actually get the values of it. Okay, so we can create a plot of it in MATLAB. Okay, and we'll use the visualization to understand how the optimization solver works. Okay, in most real world, as we said, the problems, it is not possible to create a plot like this, either because you have to sweep across multiple variables. Okay, or because it takes too long time to do it. Okay, so let's look this into the MATLAB here. Okay, let me open that example. Okay, again so this is an example. Okay, so you can see here this is the objective function that we have created. Okay, which is going to represent our equation. Okay, and the next command here, so all these greens they are comments, so they don't play a very important role here in execution. They're just there for us to understand what is going on in that section. Okay, that is the part of it. Okay, So what we can do is we can write that equation or whichever equation you want it, okay, and then we can create a mesh grid. What is mesh grid is basically, mesh grid is basically it's going to create a mesh of numbers, okay, like a matrix automatically, okay. So we have two variables here, x1 and x2 in this equation, okay. So you can clearly see that there is x1 and x2, two variables in this equation. So we need to create a 2D matrix, okay. If it was like a three variables, we would have to create a 3D matrix. What it is going to do is it is going to use all the elements of it to give inputs here in this equation and collect the output, so that you can create this plot, okay. That is what mesh grid does. The mesh grid allows you to create multiple points, okay, instead of manually sweeping across. So it's just like saying x1 is going to vary from 0 to 10, x2 is going to vary from 0 to 20, okay. But this is happening here through this command, okay. So what mesh grid is going to do is it is going to create values between -2.5 to 2.5 with a spacing of 0.1. So -2.5, -2.4, like that till 2.5 in both the x1 and x2 variables, okay. This is what it does. And then the next task is we are going to evaluate all the function values at all these points. So you're seeing I am going across two for loops. So there are two for loops, one for x1, one for x2, okay. That is what we are doing, and at every point we are evaluating what is the value of that function, okay, and we are storing it in variable called z, okay. So eventually what we'll have is basically a x, y, and z variables. So x, y inputs, z output, okay. So basically we'll be able to create a 3D plot, okay, of that two variable function, okay. So let's look at it. So what I'll do is go on top and run section by section here. Executed that, executed this. This is what we get, okay. So you can see here. So these are the x values, and what you can see is it's ranging from -2.5 to 2.5, and again here from here -2.5 to 2.5, okay. And accordingly we have the z variables, so functional output, okay. So if we are able to do this in real life, we would actually be able to tell you that what is the minimum function value of this, okay. How? I can just go to rotate this plot. That is also one of the useful feature of this plot in MATLAB. It is not just 2D plot. You can rotate it. Again, if you had to do this in your tool, it will take a lot of efforts to do that, okay. Now if you can see, I can rotate this plot, okay, in different axes, okay. If you want to see it in a particular axis, you can just go to some particular view also. If you want to look at it from Z perspective, so I can look at it from XY, okay. So it looks like a plane because I'm looking from top. So I can just see a sheet, and all these colors signify where the values are less and more, okay. And if I look at it from X and Z perspective, this is from the Y side, okay. And we can clearly see that the minimum is somewhere here, okay. That is the place where our minima is, okay. So we can visually find this also, okay. But this is not a realistic case, okay. So okay, so we had plotted this. Let's minimize it, okay. Now what we want to do is we want to create like upper bounds and lower bounds of our constraints. So we can create lower bounds and upper bounds saying the values of minima and maximum that we are looking at cannot go below -2.5 and cannot go above 2.5 for both the variables, okay. And then we are going to set up our optimization problem, okay. So we are going to use again same function options. So, okay, it's going to use optim tool at the back. Okay, this function allows you to put all the arguments to it. For example, what is the solver we are using here? We are using fmincon. Okay, we are trying to search the minimum value. Okay, constraint function. We want to display the iterations. And what is the output function? It's plot update. That is what we want. Okay, and if you want to give specific inputs for your fmincon solver, that also you can give here using fmincon. Okay, so it takes in what is your function, objective function, which is our logarithmic function that we started with. Okay, and what is the range that we are looking for. And so if you see all these square brackets, okay, so they basically are arguments. Okay, and if you want to look at it, how do you find how to use this function? Okay, best is you can either go to this and say help on this selection. Okay, so if you click on this, it's going to open up the fmincon usage page, and here you will see all the options here. Okay, what is the function, initial values, a, b, and what is the a equality, b equality, lower bound, upper bound. This is how you use that function. Okay, that you can explore. Okay, now we have set up this problem. Okay, and then what we are going to do is we'll see the display of function evaluation, how it progresses, the optimization itself as a whole. Okay, so let's run these two commands. Okay, so run this one and run this one. Okay, let me go. Yeah, so you saw that. So you could actually visualize that, right? But maybe at the remote centers, you might not be able to see this visualization, how it moved. Okay, I can redo it. Okay, just give me a second. But then sometimes it may be very quick and it takes time. Okay, so let me start this function, run section. Okay, so you see that. So when I click on run section, it actually starts from here and then takes this route. Okay, that is what it is doing. So what we have done is, this is normally you don't see that. Normally you don't see that because when you solve something, it gives you the final solution. Okay, that this is what the final solution is. Okay, here what we are trying to do is we are trying to see and we are trying to fetch what the solver is doing. Okay, and this is what we are trying to do. So we are displaying all the happenings of that function fmincon solve. Okay, and display the output of that function count. Okay, so what if you don't do it, it will just going to give you the final option. Okay, but just enabling this will help you see what the function is doing. Okay, I can redo it again and it does that. Okay, okay, from here. Okay, so this is what it does. Okay, now here also what I can do is, again, I can see it from different views. Okay, that's what it is like. Okay, so also it is very important sometimes to visualize how your solver is taking the approach. So that is why this part of the code is I thought will be useful. Okay, so here, be it whatever your problem, 1D, linear, non-linear, you can actually visualize what the root solver takes. Okay, and that helps you to understand some insights of your problem. Okay, now next section is basically is finite differences. As you can see, like many of the objective functions evaluations are from the finite difference calculation. Okay, fmincon does in order of like approximate gradient. This figure will actually show you all the differences. Okay, let me run this section. Yeah, where is that? Yeah. Okay, so you see that. Okay, so what is here is let me just close this and run it again. Yeah. So this is what we used earlier. Okay, this is what the points are evaluated in optimization. Okay, okay. So that's the highlighting. What is an objective and evaluated points and solver steps. Okay, so it is evaluating two points and taking a solver step whether to go in which direction. Okay, that's what it is shown here. Now let's go zoom in. Okay, so some of these points, let me slightly make this smaller. Okay, so some of these points, like if you see here plus markers in that figure, what are these is basically due to a line search step that the algorithm takes. Okay, and where it modifies the step size until it finds a satisfactory step to take. So others, like the ones you see here, you see when we will zoom in, are due to finite differences. Okay, so let's see this. Okay, let me see this. Okay. Okay, so what we'll do is we'll slightly zoom inside this part. Okay, so if you zoom in, you'll be able to see the differences where it's way too small. Okay, okay, like that. So you can explore this also. I'll give you this. You'll get this code. Okay, and yeah. Okay. So one more last step. What is to use URL supplied gradient. Okay, you can also, so some gradients the solver will calculate. You can also supply user gradients also, like how to approach that. Okay, I'll not get into that then because it may not be useful for everybody. Okay, so you can try this also at your end. Okay, all right. So this is what we understood. It is mainly like nonlinear problem, logarithmic problem. You can define the input and output. Okay, x1 and x2. What is the range of that x1 and x2? Later on, you can create the function plot. You can visualize it, and then you can also use solvers such as fmincon to basically pass those arguments of the objective function, the inputs, the inequalities, all those, and then solve that. Okay, and you'll get the final result. What is the minimum option? Okay. Now, if you take an example of it, okay, how do you apply it? So that is a mathematical. All these functions, they look mathematical. So that is what makes them slightly little boring, because you can't relate them to something in real life. Okay, so this is what I've done is related it to a real life example. Okay, so there is a crane type which is known as a gantry crane, and that's used in many places like shipyards, inside big industries, in moving heavy objects. Okay, they are suspended by cables. Okay, and one of the problems with the cables is when you move, okay, they tend to move like a pendulum. Okay, and if your precision is you want precision in your movement, and if you're carrying, let's say, like a 10 ton kind of load, and if it slightly hits your wall, it might break it. Okay, so you have to very precisely do that. Okay, so the idea is you say, then if provided we give you this problem, determine the acceleration profile of that movement here, horizontally, of that crane. Okay, how it should move. If you say I have to move 10 meter, it is our job to find out how it should move, accelerate. Okay, that minimizes payload swing. Okay, it should not swing. Okay? And you can do that. You can imagine it. For example, if you start fast and slow down, deaccelerate, you can actually minimize that. Okay, but that's just our thought. Okay, let's look at it from mathematical perspective. Okay, now how it's going to look like, if you see on your this dotted black line is basically your acceleration, velocity. Okay, and your this point, you see the solid line is your position of the crane. Okay, and this is the time in blue. and the acceleration. So here acceleration is positive for whole time, acceleration 0, and acceleration negative. You're trying to stop, okay, like that. And this is the total, I think, movement and total time, okay. But as we saw earlier, with some constraints, we will have to define here. So we can say that we can divide this problem into 3 parts: accelerating, not accelerating, and deaccelerating, because you have to follow this step. You will accelerate, and not accelerate, and deaccelerate. Okay, so these 3 inequalities will be there. Okay, which is basically for how long you have to accelerate and deaccelerate. Okay, and total time also should not be long than this. For example, if you move really slow, it will not even move. Okay, swing. So you can't take 1 hour to do that. You have to do that in let's say 20 seconds. Okay, so that is also defined here. Okay, so how do you solve that? Okay, now we have till now seen MATLAB scripts. Okay, which actually a form of MATLAB code, which is object oriented C++ kind of code. Okay, now I also want to introduce you to something different as a flavor, because you can solve things in a different way also. So this concept, the symbolic maths approach. Okay, so there is a particular way of solving maths functions is by solving them symbolically. And what does it mean is you can write programs in a more textual language. Okay, just like as you write on your paper also. Okay, so in MATLAB you can actually write those kind of symbolic equations using MuPad. Okay, I'll show you how it looks like. You can perform exact computation using familiar MATLAB commands also inside there, and you can integrate Simulink also to that, Simulink and SimScape. Okay, so let's see that. Okay, let me see if there is something more here. Okay, so let me open that. Okay, so that's it. So first I can just walk you through the whole code. Okay, so this is if you see the R variables: height of the crane, payload displacement, okay, length of first phase, okay, all the time. Okay, and this is this is your solver here. Okay, solve this crane ODE. Okay, and plot it. Okay, so this is just solving it. Okay, for this inputs. Okay, not optimization. Okay, so and we can go step by step. First we see if we choose some variables, how it is going to perform. Okay, let's see it. Okay, so if we click on this, so this is what our plot looks like. Okay, so what you can see is that this is your angle of swing, okay, of the crane. So as it is moving, so this is acceleration, stopping, and deacceleration, and this part, it is not doing anything. It is stopped because it has reached that distance. Okay, and since it has reached that distance, you see a solid graph here. What colored we have colored it? What it signifies is that it has reached this point where it has to reach, but it is still swinging. So this blue is something that we want to not happen. Okay, and this is the point where we are setting up and creating that our objective function. Okay, and what is our objective function now? To minimize these blue color. Okay, and that is the way how you approach any problem in automation, because when you start thinking about something, you can actually represent them mathematically. Okay, once you are able to represent that system in mathematical form, then you can identify what you have to minimize or maximize. Okay, so in this case, this blue color we want to maximize because it has already reached at this point of time, and it should not swing. Okay, whatever it has to do. So we have to find out the acceleration and the time. For that, this will get minimized. Okay, let's see how it's going to happen. Okay, we can also animate and see. Okay, let's see that also. Okay, that is what we are saying. Okay, so it has reached to that point and it is still swinging. Okay, I can click it again. That is what it is doing. Okay, it means that. Okay, right. So let's go ahead and set up this problem and minimize it. Okay, so we'll set this problem. Okay, and let's display that animation. Where is that? I just had a figure somewhere. Okay. So it's still optimizing it. Okay. Okay, it has found it. Okay, so it should be here. So you see now. So now, if you see, we have optimized the time and the acceleration such that the blue color zone has minimized here. Okay, it is still there, very, very less. Okay, so you see here now, this is the movement. Okay, and it goes and gets stabilized there. Okay, this is what you will be able to achieve after you have performed the optimization on that acceleration and the time, how much it has to accelerate, how much it has to deaccelerate. Okay, and if you are able to finally get those values, you can actually see it, animate it. Okay, and this is what you will be able to get. Okay, this is one application of those nonlinear optimizations that we looked at it just ago. Okay, so these are all part of, again, examples. Okay, and you can again try your own set of examples here also. How? Okay, okay. How this is animated? Okay, okay. So one question is basically how we can how we are able to do this. Okay, like this animation. This is what we are able to write this. Okay, so there are various ways to perform animations within MATLAB. So these are basically nothing but figures and scopes, whatever we have seen. You can just plot. So this is basically nothing but a plot only. Okay. So what normally we do is we can create these like circles, line, and objects. So this is basically nothing but plot. Okay. And when I run this, so this dot that is moving on this again is just a plot that is highlighted. Okay. So normally, if you see, we are getting the results first. Okay. So this is not solving as it animates. So we are basically getting all the results, storing them in the workspace, and then we are reusing those values to animate it. Okay. So we have created a function. Okay, I can open this function also. Okay. So this again nothing but a MATLAB code. So you see here, it is creating lines and circles. If you go down, okay. So this is what it is doing. Okay, setup animation. It is using. Let me open where you'll see. Okay, yeah. So if you see box, it's using box, which color, all those things. Okay. So if you look at this particular program, which is file name animate crane in this example, you can actually find out how it is done. It's not very complex. It's just if you want to move a circle in a circle, so you first need to draw a circle, move it to the next one, and erase that earlier one, and that is how it does. Okay. So here, once you are able to do that, the help also it is there. Yeah. Okay. So there also you can get it. Okay. So it's implemented in a function form. Okay. You can write your own code here also, but it takes a lot of time. Like yeah. That also you can use. Yes. Okay. So that is one we got here. Okay. Again, from here you can put inequalities also, like time and all those things, and you can even put constraints and then solve it also. Okay. Fine. Let's go here. Okay. All right. So let's come here. Okay. So now we have basically two more things. Okay, but these are things slightly going to take some more time because these are some maybe different topics to you. So I'll spend some more time here also. Okay. Fine. So we'll get into something known as mixed integer programming. Okay. Some people might have heard about it. Some may not have heard about this programming. Okay. So and some of you might be doing this, but not knowing what you are doing. Okay. That also might be possible. Okay. So, but there is a proper terminology which is named as mixed integer. And what exactly? Let's see that. Okay. So I've written some notes also. We can look at it. So let's see that first. Okay. Here. Okay. So let's think about why it might be important for a variable in an optimization problem to only take on discrete or integer amounts. For example, there are a lot of things in the real world that only exist in integer quantities. You know, for example, number of shares, number of cars. Okay, because they will take only integer values, not decimal places. Okay, let's say that, and for all these items, okay, it does not make sense for a solution to the problem to have fractional values. Okay, it can't be like 0.1, 0.2, 0.3 like that. Okay. Another common occurrence is the real world is of binary decision, which is ones and zeros. Okay, on or off like that. Also, those are also like states, discrete numbers. Okay. Mixed integer programming gives us a way to solve linear optimization problems with constraints and specify that certain variables must come out to be integers. Okay, so we saw earlier C1 coefficients, they came out as floating points. We even use these times also, saying 2.1 seconds. Okay, but if we say explicitly that we don't want decimal places, we only want integers, we can also do that. That is where this is important. So if you say I want to maximize number of cars on the road, you cannot say it is 1.2. It has to be 1 or 2, like that. Okay. More formally, we have a linear objective function subject to linear inequality also. That also I'll show you. Okay, this one here. So you can have a continuous and integer variables or linear objective and constraints in it, in this mixed integer linear programming. Okay, let me even show you here. Okay, this we have already looked at it. So what type of integers can happen? Okay, ones and zeros. This is what two things are part of this mixed integer linear programming: continuous integer variables and linear objective constraints. Okay, so let me do one more thing here. Okay, just give me a second. So I'll open up one of the examples from here. Oh, sorry, not this one. Where is my examples? Yeah, this one. Okay, right. Let's go back. Okay, fine. Okay, so what is that mixed integer, let's say, problem also? Okay, so again, like we saw, we took a nonlinear optimization problem into a gantry chain, okay, or application of it. Again, this kind of problem, what are the applications? One example is here, which is very popular, traveling salesman problem. Everybody might have heard about this problem. Okay, and in this problem, the definition is that we have to find the shortest path through multiple points. Okay, so it's like we have to visit 10 cities, and they have a distance between them, and we can't go to a city again. Okay, so you have to visit only once, and you have to find the shortest possible path. Okay, that is what the problem is. Solution is to calculate distances between all combination of points and do it. Okay, and what we can do is solve an optimization problem where variables correspond to trips between 2 points. Okay, so for example here, if there is a trip, it says 1 here. Okay, If there is no trip, it says 0. Okay, like that. So let's look at this also. Let me go into this. So this is a very classical example. Okay, let me open that. Okay. Yes. Okay. So again, this example inside this program will cover different ways to solve this problem. Okay, but we'll look at this first way, and then you can just browse through other ways also inside this. Okay. So this shows how to use binary integer programming to solve this classical example of traveling salesman. Okay. This problem involves finding shortest closed tour. Okay. In this case, we are finding a closed path. Okay. That means you are going to go and come back. Okay. Through set of cities. Okay. In this case, there are 27 stops, 27 cities we have to go. We'll also solve this initial problem and see that the solution has subtours. Okay. So that means you are going again to one city, more than one. This means the optimal solution found does not give one continuous path through all the points, but instead has several disconnected loops. Okay. So what we'll do then is to use iterative process to determine subtours, adding constraints and rerunning optimization. Okay. So what we'll see is that if such kind of problems happen, okay, we can see that what kind of constraints we need to add to make the problem optimization much more better. Okay, that is very important. Okay, otherwise we'll get into a solution which may not be relevant to us. Okay, so let's look at this. Okay, now what we are doing is we are using a latitude longitude. So this theoretical problem you might have read in books or any other class, but they show it normally on a distance noted or points. Okay, but to make it more realistic, what you've done is put latitude, longitude, and exactly saying what are the places we are going to go. Okay, so we are using here that lat long data, and we are using a mapping way to just put all these cities on that let's say web maps. So these are all part of in MATLAB functions inside, and you can use them directly. Okay, it's also called I forgot the name of that toolbox. Okay, so that allows you to integrate the maps and lat long data with MATLAB. Okay, and if you want to know which one is it, okay, so let me show it to you. Okay, let me open that. So what you can do is go to help. You'll see all the toolboxes here. Okay, it's okay. So it's not got all the one, but there is one which works with maps. Just like Open Maps, Google Maps, things like that, and you can use them. Okay. Yeah. Okay. So it's going to. So what it is doing is, it needs web map to load that map data and show you all the things. If you go into the help of it, what you can do is you can. Okay, so it won't be there. It's called mapping toolbox. Okay. Let me show it to you on the net if it is available. Okay. All right. So let me show it to you here. Okay. So if I go to internet and you say MATLAB mapping toolbox, okay. This is what it does. Okay. So web map is a part of this toolbox. Okay, that is why this toolbox is not installed here. Okay, this mapping toolbox. Otherwise, we could see it. What you can also do is you can also search for this problem here. Okay, we can't run it, but we can see this problem: traveling salesman. Okay, that is here. Okay. Again, if you see, this problem is a shipping example. If you have the toolbox with you, okay. So here you see so many cities. There are around 200 stops. Okay. So there are 200 stops that we want to make. Okay, and we want to find the shortest one. Okay. So again, this is a mixed integer linear programming. Okay, we are going to use the same approach. Okay, and we want to basically, if you see, we are using again optimization toolbox to find out the distance. So we are setting up the objective function here, which is basically we just take pick all the options. We do permutation combination, or we say if you go from these points, this will be the distance. Okay. Once we set that objective problem, we give it to the optimization function and set your constraints on it, saying your city cannot visit more than once. Okay, only once it can be there. So then once you give all these objective functions here, linear equalities, constraints, it is going to give you a result. Okay, and then you can visualize those results. Okay, and how you can actually plot them back. Okay, so this is what your plot would be. Okay, so what does it mean is, in this plot, what you can see is that it is visiting all the cities. Okay, but what is the problem? Let me minimize this guy. Okay, that you're just doing subtours. You are visiting all cities. This is a, so that is the difference between a real life problem and a maths problem. Okay, so you say mathematically I found a solution, but does it make sense in reality? It could be no also, because if a salesman is going in these 6 cities, okay, how would he directly go to here? Okay, he cannot just disappear and appear here. Okay, so he has to actually go like this as a path. Okay, so that path is not there. So mathematically there is a solution. Physically, technically, it's not realistic problem. Okay, so that means now we have to add right set of constraints here. Okay, otherwise we will going to get these kind of answers, and they will not be realistic in the sense. Okay, so that is what is important. It has to be like this. If you see this path, it is going like this, like that. Okay, that is the realistic path. These subtours, these are subtours which are not realistic. Okay, so what we'll do is we go into this, we add subtour constraints. Okay, that means you are constraining the search to not go look for subtours. Okay, we are trying to avoid subtours from here. Okay, so what we are doing is creating another function. Okay, we are saying let's create functions. We are going to find out what is the length of that tours. Okay, and we can just create total number of subtours. It has found out that 27, and we can just make them 0. Okay, that is what we are trying to do. Okay, so once you are able to reduce them, you will get something like this. Okay, so you say subtours have to go to 0. Okay, or let's say 1. Okay, only one tour has to happen. Okay, now here all those subtours are removed. Okay, now this is more realistically possible, because you can see here, this is all one tour only. It's not going to just have any subtour now. Okay, so this is more realistic. Okay, you can also see what is the solution quality of it. The solution, is it feasible tour or not? Okay, because it should be a single closed loop. You cannot just go from one point to another point and stay there. You have to come back also. Okay, that is also what you would like to do. Okay, another aspect of optimization, which is global optimization problems. Okay, what type of problems are these? Okay, so why does the fmincon have hard time finding the function minimum? Okay, so if you see on this, so there are some functions that we have plotted here. Okay, and if you start at 0, so these are two functions, so they have multiple maxima and minima in this region. Okay, so if you start at 0, okay, and you'll find this as a minima. Okay, and if you start at 1, you'll find it here. Starting at 3, you'll find it here. Okay, minima. Okay, why what is happening is, and you see the same another function here. Oh, sorry. Okay. So if you do that, So let me just open that slightly. Okay, so you got the idea. So there are multiple minima here and multiple maxima, but within this range there is one global maximum, one global minimum. Okay, that is we are interested in. Okay, so if you look at a starting, so all these solvers, okay, like f min con, you have to give an initial guess somewhere. Okay, when you take a guess and it starts going along the gradient or path, okay, it might actually just find a local minima and stay there. It says, okay, I found it. Okay, because what it does, it's like a hill, you know, it goes like ups and downs. Okay, and if I say find out where you are the lowest, if you find the first lowest, you'll say, okay, this is my lowest point. But it might be that if you go further, there is some other lower point. Okay? That is the difference between the local and the global minimum maximum. Okay, so let's say, why didn't this function find that maximum efficiency? That is also very important here. Okay? So if we run this fmin unc, okay, on this particular example, you see the start point and then it goes and comes here. Okay, let me slightly zoom this, okay, so that you can see it. Okay. So inside here, uh, there is the minima lies here. Okay, that's our minimum. Okay, now what has happened is when we ran the fmin con, okay, it went through this path. Okay, so as we saw from our previous examples, the solver follows a particular path based on where the values are, you know, let's say going down, decreasing, things like that. Okay, now it since it followed this path, it actually came across this point, which is minima for it, and it's not going and uh, and if you see along that minima, there is some maximum in front of it. Okay, so it has stopped there. Okay, and it is not able to reach this point because it's like there is a boundary and you can't see beyond it, but there is another minima on the other side. Okay, that is why it has stopped at this location. Okay, at this particular location. Okay, so it's very important that we sometime, if we know where, if the problem still has not found the real minima or the maxima, you should use a global optimization methods to basically find your minimum maximum. Okay, so right. So for example, why didn't nonlinear regression find a good fit here? Okay, so here, so there are certain points again. So I'm taking different examples. So some certain points we did curve fitting. Okay, but here when we did nonlinear regression, we did not get a good fit because there are 2 points. Okay, which are not along with this. Okay, again in this case, same analogy, you know, that it could not see it, and it's not fitting over there also. Okay? So what is the job of this, let's say, global optimization as a task? Okay, so what we want to do is find out the lowest or the largest value of a nonlinear function that has many local minima and maxima. Okay, that is what we want to do. Okay, so problem, so we want to do that, but what is the hurdle and challenge here? Okay, traditional solvers often return one of the local minima, not the global. Okay, this is what normally all these local solvers do. Okay, now how we can achieve this is by using a globally optimal solution. Okay, a solver that generates that global maximum minimum. That is also what we want to do here. Okay, so global optimized solvers that are covered, you know, today what we'll be doing is something known as multi-start. Okay, how would you find that? Okay, you can start multiple locations. Okay, multi-start, global search, simulated annealing, pattern search, genetic algorithm. Okay, so these are you know, the top 5. There are others also, but these are the most popular ones. Okay, and these are very useful because most of the time when you have a complex problem, if the path of the solver that it takes to find the minima does not see that global minima, it might not be able to find that. Okay, and you might not get the best optimal solution. Okay? So these are five algorithms that we'll see one by one. Okay. So for example, if you see multi-start, okay, non-linear regression, multi-start non-linear regression. Okay. So what if you see? Let me zoom it slightly. Okay. So this is a curve fitting standard. You know what we saw earlier. Okay. It is you can run it by LSQ curve fit. Okay. So here, what is happening is there is a starting value and there is a final value here, and then we are able to get a curve fit here. Okay. Now if you see, we missed a few points here. Okay. And there is let me see mouse here. Yeah. Okay. So you see this point and these 2 points are not covered here. Okay. How do you overcome this challenge? Okay. Because these are traditional solvers, they are not able to find those points. Okay. So what we do is we do multi-start. Okay. So if you do a multi-start solution, what you will see is that we will be able to cover those points as well. Okay. And how do you use this? Let's see that. Okay. So what is a multi-start? Okay. So we basically run a local solver from each set of start points. Okay. So you can select start points and we can run those local solvers itself from multiple locations. That is what we want to do. Okay. Also, there are options to filter starting points based on feasibility. Okay, so you can check whether this is feasible or not. You can also filter the starting points, so you can reduce and make it faster. You can also do parallel computing on it. Okay, since you are solving the same problem through multiple start points. Okay, this is a perfect example for parallelizing your task. Okay, so you can give so you have multi-core CPUs, you have clusters, HPC, high performance computing machines. Okay, so they have multiple processors inside that. Okay, so they have like probably 8 cores, 16 cores, 32. Or if you have a big cluster in your institute, you can also parallelize that to 1,000 times also. Okay? So what you can do is you can parallelize them also. Okay. So let's take one example here. Okay. So if you take this example, multi-start demo. Okay. So what here is, you will see that multiple peaks are there. Okay. There are multiple peaks, and this one here. Okay. And you'll see some locations here I've mentioned. Okay. So start, end, start, end, start, end. Okay. So what does it signify is that I'll show you this in MATLAB also. So if I start at a particular point, where will I end it, and what path I will follow? Okay. So that will you will be able to understand clearly how this concept actually can solve this problem. Okay. Let's look at it. Okay. So I'll go to MATLAB here and open our multi-start. Okay. So let's look at multi-start. Yeah, nonlinear regression. Okay. So what we'll do is that's clear. This is what we said. Okay. The first is we'll clear and close. Okay. What does these three commands do? Close all the graphs that are closed, close, clear, workspace, and CLC, clear the command prompt. Okay. So let's run one by one, run this and run that. Okay. So this is the one that we were seeing it. Okay. So these are plot. This is what we started with. If you try to do this with the linear curve fitting, you will get an exponential curve, but you'll not be able to cover all the points. Okay. That's because they are not designed to achieve this. Okay. Let's look at some more. Okay. Then here what we'll do is we'll define our problem statement. Okay. This optimization. So we are using LSQ curve fit. If you want to know more on it, let's get help on this. Okay. Okay. And what this solver does is it solves non-linear curve fitting problems in least square scenes. Okay. So this is basically a data fitting algorithm. Okay. So what it does is It works specifically on nonlinear curve fitting data. So if you have a nonlinear data, use this one, not the other one, which we saw earlier. Okay, so that will give you, but this will give you better results. Okay, so let's see it. Okay, how it gives results. Oh, sorry, maybe there is newer one. Okay, let's see. We got some error here. Let's see what was the error. Okay, undefined function or your model. Where is it? Where I'm using. Let me give me a moment. Objective is here. Yeah. Okay. I did not run this function here. Okay. I just came directly here. I have to run this objective function. Okay. This function has to be written here. Okay. Then it will run. Okay. So what will happen is, just a second. Yeah. So if you see function create optim problem, it is okay. Let's run it from again. It is only because we are not running all the functions. Okay. So let's go again. Run. Run. Okay. Run. Run. Okay. Oh, okay, okay. So it could be. Let me see in my this MATLAB what toolboxes are there. Okay. It could be that that particular. Okay, neural network is there. Fuzzy logic. MATLAB. Yeah. Now to see. So it's create this particular variable. It's giving me a problem here. I have to create optim problem. It's using some function which is not installed currently here. That is why it's not showing this function. Okay, it's a part of particular toolbox. Okay, but if once you get it, you can actually do it. So eventually, what will happen is we'll actually solve this using this function. Okay, we'll put this there and we say solve this problem, this one. Okay. So we are what we are trying to do here is do a curve fitting on that point, but a nonlinear curve fitting. Okay, that is what. So this is only for curve fitting. Okay, let's look at the multi-start here. Let's look at this one here. It's going to take. Okay, so this requires particular. Let me just see. I think this was introduced later from this version. It uses RGB, otherwise I would have showed you. Okay, so what you will do is what you can do is once you get these files, try to run this, and better would be to run it on MATLAB, which is 16B onwards. Because some of these functions were not there at that time. Okay, so I can even specifically look for it also. Okay, let me just see it. Okay, so if you see when I search for it, it's not there. Okay, but if you go online, you can actually see that. Okay, so let's say go to MATLAB and multi-start. Okay, so that's what it does. Okay. Multi-start. We can even find out, I mean, which particular toolbox it requires. Okay. So you see, it needs this particular tool. That's why we can't use it. So there is a global optimization toolbox. Okay, that is required to run this. Okay, and in our license we don't have that actually. So if you see here, this is our license profile. Okay, MATLAB Swimming, but there's no global optimization toolbox here, so we can't use it. But this is how it runs. Okay, I'll just walk you through the. Okay, this is very good. We can even see it here. whole method. Okay. So multi-start, what it does is generate starting points, run start points, generate global optimum solution vector. Okay. So basically nothing but what it does is it selects multiple start points. Okay, and it finds out what minimas have been found. Okay, and the last step, global optimum solutions vector. Okay, this last one will give you, based on all these finding, what is the global minimum or maximum, like that. Okay. On the other hand, if you are using a global search algorithm, this is slightly different. Okay, that will also cover on it. Okay, let's go here. But all these programs, just go through it when you get it. Okay, install the global optimization toolbox, and you will be able to run this. So the idea is very simple. Okay, you can create this object ms. So ms equals to multi-start. Okay, ms dot display iteration. That means when this algorithm starts, display all the iterations that are happening. TIC is timing. So when you say tick, your timer starts. Okay, and you then say give a parameter of RNG to default, and then you start running this. So run ms, the problem, and 50 iterations. Okay, like that. Okay, and you will get output, solution, values, everything. And serial time is equal to talk. What that means is between tick and talk, you can calculate how much time it has taken. So you are trying to see how much time it is taking, so that you can. Do you want to run it on a cluster or something like that? If it is taking too much time, okay. And then what you can do is visualize it. Visualize the best solution. So what you could do is curve fit plot iterates. So whatever iterations has happened, you plot all the solutions. Okay, basically plotting all the solutions that the run has created. So you will see those plots. Okay, the ones which are like this. Okay, okay, let me open that slide. This. Okay. Okay, this one. Okay. So this kind of plot you will get. Okay. So what you will see is that you will get multi-start, different colors. Okay. So you see this yellow color start location, end, start end, all those things. Okay. You can even see that in 2D also here. Okay. So it is found that all these solutions are converging here more. Okay. This is what you can see. Okay. But what is important is, if you see on this plot, okay, this one. This is how you will look on 2D also. This is how you look in 2D. If you're looking at from 2D perspective, so these all red dots basically are nothing but start points. Okay, and where they are going is like the direction. Okay, at multiple start points. Okay? And one of this could be the actual global minimum or maximum. That the algorithm will automatically tell you this is the maximum one. Okay, or minimum. Yeah. Okay. Fine. And what is this global search? Okay. So if you see, it is like a multi-start, but it is more heuristic algorithm, and it calls fmincon from multiple start points to try and find the global minima. Okay. Filters and removes non-promising start points. Okay. So it is like a multi-start, but more refined. Okay. What it does is basically multi-start even executes all points, whether it may be relevant or not relevant. So this here also filters and automatically gives you the ones which are promising and won't go even solve it, because solving is consuming execution. It will take more time. Okay, so it is going to take more time. It's better if we can remove some solutions. We can be faster, because as you start running this, okay, what will happen is your computer will take more time to run this. Okay, because it might take, if it depends on the problem, it might take 10 minutes, 20 minutes also, like that. Okay, so it's good to filter out some start points that are not promising. Okay, now how does the global search looks like? Okay, for example, if you see, there are three peaks here. Okay, three minima. One is here, one is here, one is here. Okay, and green is at minus this, red is at minus 3, minus 6, and minus almost 0. Okay, so which is the lowest one? This minus 6, the blue one. Okay, so let's say if the run started from this point. Okay, if the run started from this point, how will it go? Okay, so let's say if it starts near to this green one, it is going to go much closer to the green one. Okay, and then it will say, okay, found the minima, which is on the green one. Okay, in this region. But what if happen is in the global search algorithm, stage one, what will happen is it's going to create some start points. Okay, as you can see here. Okay, then it's going to select few which are not relevant, probably remove them or use them as the starting point. Okay, so here if you use this one, for example, okay, so it's going to go with the towards the red one. Okay, that is also something that is important. Okay, so you start at multiple locations, and then because if you don't use multiple start points, you will probably get one of these. But if you start populating points, okay, and then selecting which minimas you're getting, you can start removing some points. Okay, now if you again populate some points, okay, you'll see some points you don't need to consider. What are those points? Are basically this point, this point, this point, because if you use them, they are just going to take time and give you red or green only, which is already you have found out. Okay, so what we do is take this one. Okay, remove that. Okay, take another one outside. Okay, so if you see what is the current penalty threshold value, that also we can calculate. So all this is based on the distance. Okay, distance between them. Okay. So what we do is accordingly, the algorithm will move to a location which will be more feasible again. Okay, so it is moved to here. So let's see what will find. So it will find out this blue one. Okay. So current penalty threshold value has decreased to 2. Okay. Again, the new start point is here. Okay. So give you here. Okay. So expand basin of attraction if minimum already found. Okay. So if you have found the minimum, you can even expand that look around this region. Okay. So this is all done by the algorithm behind. You can also customize these things also from the parameters that the solver takes. Okay. I'll show you one example of it also. Okay. So here you see there is basins that can overlap. Okay. And what happens is when these basins overlap, that there is almost your search looked at all these places. Okay. 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 So let's see that. This let me see if it's going to work. It also might require global optimization. Okay. So let's open that. So that's the function. Oh, okay. So it's going to need that. So, so this is a GUI that we have created. Okay, you can also create this kind of interface. So this is done using guide tool, which is there in MATLAB. You can create this kind of tool. So this is just for us to demonstrate easily different functionality and solvers. Okay, so if I select, let's say these are the peaks. Okay, and we can also see it in 3D also. Okay, what these peaks look like. Okay, easily. So now what we are going to do is we will select a solver. We'll say, so here it won't work, I know, because we can it's not installed. Okay, so you see here it doesn't install here. But what will happen is if you had this, you can use this GUI. You will get this from this examples. Okay, so you can use this GUI to have multiple types of functions. Okay, so this will be dependent on the tools. Okay, once you have this, you can try out all these different solvers. multi-start, global search, pattern search, GA, particle storm, simulated annealing, all these. Okay, you can select all these. So it will be good to have that uh, you know global optimization toolbox installed on you. Let me see if this will run, because then if this runs, may okay again. The thing is, it is part of that. Okay. No, okay. And the launch. Okay. So there is a file that. So it's all part of those tools only. Okay, no problem. Let me show you here only. Right. So let's go here. This we have already covered. Okay. Okay. This one. Okay. So this is how it looks like. Okay. So if you see here, there are some start points here. Okay. And based on these two start points, it has found out that this is your global minima. Okay. This is your global minima. Now another method is, as we saw, it was known as simulated annealing. Okay. What is that approach? Let's see that. So it's a probabilistic, again heuristic, but meta heuristic approach based upon the physical process of annealing in metallurgy. Annealing is a lot of people who are from metallurgy background, mechanical background. They might have seen this process called annealing. Okay, so it's a process done on metals to make them harder, or let's say align all those grains inside the metal. So you heat them, you cool them, heat, cool. So it makes the metal more all the grains align and stronger. Okay. So now here is controlled cooling of a metal allows atoms to realign from random higher energy state to an ordered crystalline lower energy state. So how it's going to help is basically that it's going to give you a more stronger metal. But in this case, how we use it? We use that functionality to basically find an minima of a global problem, global minima of that problem. Okay. So how it works is, okay. Let's see that. Okay. So we are using the same problem, three minimas. Okay. And run from a some point, let's say starting point x is equal to 0. Okay. So we say, so here instead we have introduced another term, which is a temperature. Okay. If you put a temperature T is equal to 1, okay, what we are trying to say is that it is going to generate an envelope. Okay, it is going to generate an envelope, and within that envelope, okay, it will show you possible new points. Okay, based on the normalization and the temperature. It's a kind of a normalization if you see around it. Around this point, it's going to get some points around it. Okay, normalized points. Okay. So what is going to be next is it's going to take one more point. Okay, let's see that. Okay, okay. Let me go slightly here. Yeah. Okay. So what you see is the default this distribution is a standard multivariate normal distribution. This one. Okay. The next point chosen is by adding a temperature times the probability in x and y to the current point. Okay. That is what is being shown here. Okay. So it's basically the probability in x and y and the temperature. Okay. So we accept this point. Okay. We take another point, get some one more point there. That is what we are doing. Okay. Let me show you all the details. Okay. So we will also calculate acceptance probability shown here to be 11%. Okay. So this is now probability is 11%. Okay. That is what we are getting here. Okay. Then this is rather kind of a low probability. So we'll assume this point is not accepted. Okay. And then let's take, we will add few new points and evaluate them. Okay. We will evaluate, let's say, this point. We will evaluate another point in another opposite direction. Let's calculate this probability here. Okay. In this case, it is accepted since it's lower than the current point. Okay. If you calculate the probability of this, okay. Lower temperature according to temperature schedule and generate new points. Okay. So this is what we are trying to do. Okay. So if you see, based on the we based on temperature, okay, distribution around it, what we are trying to do is we are moving along different points in different direction, and we are trying to calculate what is the probability of finding a minima in that direction. Okay, that is what we are doing from this function. Yeah. Okay. Yeah. Yeah. Okay. So that's a good question. Okay. So if you see here, let me. Where was it? Okay. Here. Okay. So what it does is, if you see, um, overall it creates few points. Okay. And as in the annealing process, what happens is those crystals are in different directions. Okay. So it's like, if you have a standard metal, if annealing is not done, they are in different directions. So because of different directions of crystals, it is easy to break. You can break it. But if you have all aligned crystals, when you have annealing done, they make it very, very strong. Okay. So the how annealing gets into this algorithm is basically, what it tells you is that when you do the annealing, they get aligned into certain direction. So the direction is something that what matters a lot here. So direction of the crystals. Okay. In this case, it is the direction of our approach. You know. So what we say, we start a point, but direction becomes very important. Which direction should we go, like that. So that is the analogy that they have connected. The developer of this algorithm. Okay. So if you see, it filters non-promising start points. Okay. So basically, if you take a point, if it has to be evaluated or not, this is evaluated using that probability of, let's say, annealing, whether this direction, if I go, does it make sense, or the other direction. If it is not a valid point, it will remove that. Okay. So based on the local minimum found already, next starting point, proximity to the local minimum found. Okay. So what it is trying to do is, so if you select a point and if you did not find something in that region, in that direction, so it will kind of remove that region altogether as a lookout point next time. Okay, that is what, if you see. So next starting point, sample proximity to the local minimum found, like that. Okay, and that is what we are trying to do here. Okay, so this is what the default distribution looks like. We start point, and when we move across that particular direction, okay, we select a point, and what we will get is, we will get a probability along that, because what is happening is, so the start temperature is 1, and as you go along the surface, temperature goes down to 0. Okay, like that. Okay. So that is what is happening here. Okay, so we start with this center point. Temperature is 1 at this point. Okay, so if you go till here, okay, do you see this 0.9 and 0.72? This is like a 3D surface. Okay, so as you move along x and y, you will basically have probability along it. Okay, and the probability will decrease because it's a normal distribution as you go along this. Okay, so as you go to here, probably at this point, x and y probability is this into the temperature will give you probability of this. Let me show it to you. Okay, this one. It's not visible. Okay, let me slightly make it higher. Okay, this one. Okay, you see here. If we know that at this point, uh, the probability will be around 11%, okay, which is low. So you remove this point, okay, like that. Okay, so it's more on the direction and the temperature. Like if you put a temperature to a surface, it basically spreads across in a exponential form and drops down. Okay, if it is 100 in the center, it will go down to 50 degrees uh, evenly across as exponentially. Okay, and all these temperatures, why this is exponentially is because heat and all these different natural way of conduction, they happen exponentially. They don't have linear form. Okay? That's why it is all exponential. Okay? So overall, what it tells you is that if you keep doing this, okay, continuously, you will be able to find what are the points which are good to start. Okay, so everything around global optimization search is focused around multi-start and filtering points that you don't want to use them. You know, so here also if you see multi-start or global search, they are all starting points, different starting points. But it's only what is varying is the way these points are selected, which points should be ignored. That's the difference between each of them. Okay? So people have defined different various algorithms to help you do multi-start. That is the whole idea. If you don't use any of these algorithms, probably you will get the same answer, but in a more time, longer time. That is what is important. Okay. So here, if you see, when we selected this point here, we started with this, selected this. Probability was low. We selected this point and moved here. We got probability slightly higher, 0.27. Okay. Like that. So if you keep doing that, what we will do is we'll get another one and we'll get this even higher probability here. Okay, this is the value of the local minimum, but we'll get higher probability here. Okay, this is what simulated annealing does. You know, it's much faster, okay, than other approaches that you've seen multi-start. Okay, and if you see the program, you know, that we use that is there already. Once you will get this, okay, what you can do is you can actually click on this. Okay, global optimization for peaks function, multi-start, pattern search, GA, all these. Okay, so here you will be able to execute all these functions and you will get graphs like this. Okay, so here the same peaks. If you see how simulated annealing worked here, this is how you will see the process. You know, how all the steps and in the middle. Okay, and it will come to this point. Okay, which you can see here. This point. Okay, it took different approaches, and it came very close to this point. And you see some points here. Okay, these are nothing but start points and end points. Okay, all these, so they are marked with a diamond shape. Okay, that is just to mark them like crystals, like that. Okay, so why diamond? Because they are also giving you directions to it. Okay, which direction they are pointing to from start to end. Okay, so overall, if you don't want to get into the details of it, it is just a more efficient way to do global search of the minimum. Okay. Another one is pattern search, which is a direct search also. What kind of approach is? So it's an approach that uses a pattern of search directions around the existing point. Okay. So you take a point, you look around it, and you find a pattern and you then move along it. Okay. And then what you can do is you can expand contracts around the current point when a solution is found. Okay, does not rely on gradients. Okay, work on smooth and non-smooth problems. Okay, so it's not something that relies on gradient. Okay, it won't look for gradients there. Okay, that is what it signifies. Okay, so if you see here, this is let's say one point that we select. If we select this point, we go in this direction. We find very few points that are minimum qualified. Okay, but if we move along this point, we find one here. This is the end, but one here somewhere around this. Okay, so it has found, if you find a pattern, that can also reduce the number of iterations that will happen. Okay, so how does that pattern search look on the same problem?
Okay, if we look at the same problem, so there are, let's say, if you take four directions to it. Okay, if you take four directions from this point 3, okay, we can create a pattern which is a vector which goes in all four directions. Okay? And then according to the mesh size and the pattern vector, we can create the new point. Okay, so the first pole is basically this one. Okay, first pole successful here. There is if you see, let me see this. Let me calculate this more details. Yeah, okay. Right, like this one here. Okay. Okay. So what you do is yeah. Okay. So based on our directions that we have chosen here. Okay. What we are trying to do is we take this point, 1 point. So how did this point come? Okay. So we take 3. Okay, and we say they're all 1 unit away from each other. And how this new point is calculated is mesh size. What is our point mesh number of units? Between the distance between two points. Okay, and what is the pattern vector plus the starting point. That will give you a new point. So these points are a new point that has been calculated using this formula. Okay, and it will give you. So these are all internal workings. You won't have to get into the details of it, but just to showcase you what it does. Okay. So first pole is at 2.8. Okay, but you see 0.04, which is very less. Okay, so it's a complete pole, not default. Okay, so it has taken starting from here, but if you see this value is very less compared to all four values. So you start from this 4 branches, you find out which is the lowest one. Okay, so that direction, you know that there is something happening. Okay, so you can even go further. Okay, so you can take that as a next point and expand the scope even further. Okay, now what you will find is that this is even lesser. So a complete pole is here. Okay. And if you start again on the first one and again expand the scope, you'll see that there are 3 points here, 0.4, these two. So you'll see that again it is increasing. Okay, so it does not make sense again. So it will stop the algorithm. Okay, so what you will see is that uh, if this was the case that this red color was minimum, global minimum, and what would have happened is when you did this -4 would be here because this was the global maximum. Okay, so what it will do is it will move to this point next time. Okay, this is how it works. Okay. And then when you visualize this in that MATLAB program, this is how it will look like. Okay, so you can see here. So that this was our starting point. It has moved in all these 4 directions. What it has found out that this direction is better. Okay, so this was the next point selected. Again, it has moved out in another direction. It has found out that this point is better. Okay, then it has moved this way like that. So you'll see always it's a very like a straight line pattern. Okay, very straight line pattern. So if I show it to you here, let me. I think it was even visible there also. Yeah. So here. Okay. So what you can see is here. If you this is your starting point, you move along all directions. You say this is the lower value. You select this first. You came to this point. Okay, from here because this is higher. This is lower. You select this point. You move across this and this. You select this point is lower. Then move across this. So it starts getting narrower and narrower and narrower, and until you won't find any change. So that will give you the global minimum of this. Okay, right? So okay. Okay. Now, if you want to apply this also to, let's say, some application, if you see pattern search, let's say if you know the terrain data of a mountain or a location, you can even find out like what is the shortest path, easiest path, okay, highest point, lowest point, all that. Okay, that is what. So this example is also here along with this. So you can find this example here. So once you get these slides, you open this pattern search Mount Washington. Okay, this example you can do it. Right. Okay. Okay. So you can try it. Now this is the particle swarm. Okay. Now a collection of particles, what is which is moving to a region is like a swarm. Like its name has come from like birds flying together, like that. So particles have a velocity and are affected by the other particles in the swarm. Okay, does not rely on gradients again, works on smooth, non-smooth problems. Okay, so here it's like initialize particle locations and velocities, evaluate all locations. Okay, update velocities for each particle. Okay, best particle for this location, previous velocity, best location for neighbor particles. Okay, like that. So new velocity will be calculated based on the terrain, which is your minima locally at each particle. Okay, and as you see the movement along based on the values, you will generate new velocities based on the terrain. So you will see that it starts getting closer to the global minima here. Okay, that is what will happen. So it's like 10 particles as they move along this, but are not on a plane because they are on a local minimas or everywhere. So their velocity will change over the distance along with them, which is closer to the uh, global minima. The velocity will gradient will be higher. So what will happen is all the particles will come start getting closer to that particle because of the change is more in that direction. Okay, so that is what the particle swarm does to your search. Okay, so again these are different algorithm. They are doing the same thing. Okay, based on speed, based on the type of problem, you can use it. Okay, and this is the last one, which is genetic algorithm, which uses concepts from evolutionary biology. Okay, so it starts with an initial generation of candidate solutions that are tested against the objective function. So it's like evolving points through genetic approach, not like through velocities or the distance or the probability as we saw earlier. This is different. It is more. There is again a math function behind it, which it does evolution of those next generation of particles. Okay, that's why it is named as genetic algorithm. Okay, so how it evolves is basically if you take a binary case. So let's say selection, retain the best performing bit strings from one generation to the next. Okay, favor these for reproduction. You know, for example, this is a parent bit. Okay, this is parent two. Okay, the crossover will be something like that. Okay, so if you do this, okay, and this is the child. The child will have one here, both ones. Okay, where both are ones, will have one, and also one from parent one and one from parent two, like that. Okay, so this is the internal workings of that particular genetic algorithm. Okay, so it will create a child, and from this child, your mutations will happen. Okay, so it will pass on the information from one generation to the another generation to the other generation, like that. So this is used in not only this case optimization; it can be also used in multiple scenarios also. Okay. So if you again everywhere we do a multi-start, but when we come to selection and movement of the new points, we do let's say evaluate initial population. Okay, these are population initial population. So in this case, we instead of calling them as points, we call them population because they are considered to be people. Okay, so select a few good solutions for let's say next generation of reproduction. So that's what you're learning: parent one, parent two, like that. Okay, so based on uh, that selection, you will create another population. Okay, you will generate new population and evaluate them. Okay, again you select some more points here. Okay, and again create a new population. Okay, again select some points, again create a new population. Okay. So how it is happening is, if you see in real world also it happens. So if there are three big cities, okay, uh, then what will happen is there will be more chances of something being developed within that vicinity. Okay, that is what the idea is. So if you have a good population at these locations, there is something happening in this range. So it is basically nothing but global minima. Okay, that is what we are doing there. Okay, okay. So this is what it will find out. Okay. Now, if you want to use this also, this this kind of graph, it will come in this example. If you see here, the genetic algorithm here, I think this should work because this is already installed. Okay. So let's see that the temperature and data plot desired curve. Okay. This is the target curve that we want to achieve. Let's say this is for a resistor. Okay, it's a circuit design. Okay. This is let's say we want to fit this curve. Okay. Then let's run this part. Okay. Display available register sizes. Is it showing or not? Oh, okay. Here it is showing that. Okay. Uh, let's create a new data. Hold on. Okay. Okay. Target values here. Okay. Run bounds. Okay. We have defined this. Let me run that. It again uses the one function which is not there. Okay. GA. Okay. Again, so if you see global optimization, genetic algorithm, and optimization toolbox, they're all related to each other. Okay. So some functions are in one either toolbox, some in other. It's good to have all these toolboxes along with that, so that you don't miss out on any function. Again, we have one of the tools missing here, so no problem. You can run it again here. But eventually, what will happen is you will be able to run this same example, what we are showing in the slides. Okay. You can run this example and you can walk one step at a time. And if you want to reuse it for your function, change the objective function, put your objective function and start using it. Okay. This one. So okay, so this is about putting an integer constraints inside genetic algorithm. So for example, what we can do is only certain size of components are available and can only purchase whole shares of stock. So what it means is that you say you're optimizing some circuit or some mechanical design or something, and you have certain types of sizes available in market. For example, if you say 1 mm, 2 mm, 3 mm, if your algorithm gives 1.2, what should you do? Okay, 1.5. So you can also put again here same concept of integers constraints. So it will give you answer in integer form. Okay. For example, it is a register. It says what value of register should I use, to do that. So there are standard register sizes. Okay, like that. So you can use it, or you can purchase whole shares of stock. Okay, so 10,000 quantity, 20,000 quantity, like that. You can also feed that information. Okay, this is what I was talking about. So you can apply it to even a circuit. Okay, genetic algorithm. Once you know the optimization routines and algorithms, how do you apply it? Okay, so you will see these kind of problems very common in your daily life. For example, this one is from electrical area. So there is a thermistor circuit here. Okay, these are thermistors. So they change resistance over temperature. Okay, so 6 components to size. Okay, and they are in this form. Okay, they are not like 300, 310, 102, like that. They are in some forms. Okay, these resistance varies nonlinear with temperature. Okay, and this is what we were trying to do. There is an objective temperature and voltage curve. Okay, this is what we want to achieve. Okay, so this example is already there in the GA example, what we said. Okay. So this is what solvers we have: global optimization toolbox solvers, global search, multi start, well suited for smooth objective functions, returns location of local and global minima. Okay, GA simulated annealing. Okay, many functions evaluations to the samples search space. Work on both smooth and non-smooth problems. Pattern search, fewer functions evaluation. Do not rely on gradient calculation. Works on smooth and non-smooth. Okay, so you have multiple types of global optimization solvers you can use based on your particular needs. Okay. Again, what you can do is these are all multiple start problems running the same objective function. So you will end up taking more time in solving these. So you can also speed them up using parallel computing. Okay, so you can use this command here. Okay, so this is called as par for command. Okay, so if you use this, you can actually speed up your speed of optimization. Okay, so if your computer has got 4 cores, 8 cores, 2 cores, it will speed up that many times. Okay, that is how the analogy is. So you can on your laptop also you can do that, or over a big cluster also you can speed up. Okay, that is what we are showing. Okay, so clusters are typically you can find it in computer center. They have a lot of machines connected together, and you can have 1,000, 2,000 cores there. So speed up is very, very large. Okay. So also, so a lot of things can be covered even further. So you can actually find out a lot of information from going through some of these links. Okay. So this slide will have all these links. So using like symbolic gradients for optimization, improving optimization performance using parallel computing. There are a lot of videos and toolboxes. Okay, this also you can go through. Okay, so to sum it up, okay, this is what we use. We can solve a wide variety of optimization problems in MATLAB: linear, nonlinear, continuous, mixed integer, smooth, not smooth. Okay, we can also find better solutions to multiple minima and non-smooth problems using global optimization. Okay. And we can also use symbolic math for setting up problems, automatically calculating gradients. Okay. And to speed up, we can also use parallel computing within built-in MATLAB using par for command to speed up the whole optimization process.